Hi. So in this screencast, we are going to work out some simplified expressions for calculating partial molar properties in binary mixtures. So binary mixtures are incredibly common systems that we'll encounter and need to model. And it just so happens for this specific case, or this special case, we can work out some simplified expressions. And so we're going to do that here. And so to motivate, what we're trying to get at is let us again let f be some arbitrary thermodynamic state function. So if f is some arbitrary thermodynamic state function, then f bar I, partial molar f of component I in my mixture is, by definition, df total dni at constant Tp and nj, right? Everything else is held constant. Or equivalently, we can replace f total with n times f. Okay, so f total, right, is my extensive f, and it's going to be a function of temperature, pressure, and the moles of each species in my system. Right? I need to know the moles of each species in my system because that'll allow me to specify or fix the composition of my system, and then also it'll allow me to fix n, right, the extent or size of my system. Okay. Well, on the other hand, f, my molar f, is just going to be a function of temperature, pressure, and composition. So typically what I'm much more interested in modeling, or say what I typically more commonly have an expression for, is my molar f. Why? Because it's independent of the size of my system, right? It's much more generally applicable. And so, f is a function of temperature, pressure, and composition. And so if I were to pull a random equation on my hat, right, we typically fit equations like, f is equal to a constant times x1 times x2, right? We have expressions for f that are a function of composition, x. So now the challenge with these equations, right, so these equations based on just our definition of partial molar properties, is that if I want to calculate the partial molar, f of component I from this definition, okay, and if we said we had, binary mixture, so that f was equal to a times x1, x2, how I would go about evaluating said expression is I would have to plug in that, our definition that x1 is equal to n1 divided by n1 plus n2, right, the total moles in our system. And likewise, x2 is by definition n2 divided by n1 plus n2. Okay, so I'd have to plug those into a set expression. So to get a times n1, n2 over n1 plus n2 squared. Okay, so first I'd have to make the substitutions, and then I could take this analytic equation and work out, right, the applicable differential, right? So I could, and I guess I wouldn't even have to stop. I have to take a step further, right? This is n, all right? So n times f, all right, is going to be n1 plus n2 times f. Okay, so this would be a n1 n2 over n1 plus n2 since I'd kill one of the terms. Okay, but nonetheless, I would still have to make this simplification, and then only then could I attempt to work out this analytical derivative. And if I had, say tabulated experimental data, we still have the same problem, in that typically what I'm trying to measure is my molar f as a function of composition, because this could be much more generally applicable. So using these expressions, you can do it. It's just not always, most convenient. What would be preferred is if I had expressions that involve differentials with respect to mole fractions, because those are the types of expressions or the type of data I typically have. Okay, and so what we want to go about is working out expressions. Okay, and these expressions are only going to be for the special case of a binary system in which we can calculate partial molar properties involving just differentials with respect to mole fractions. Now, if you have a system that has more than two components, a ternary system or higher, you are stuck using these equations, right? To the best of my knowledge, you are stuck using these equations where you would have to take, say, your equation for molar f in terms of mole fractions and make these molar substitutions as we did here, and then attempt to differentiate. So you can do it. It's straightforward. It's just a little cumbersome. And if you had a excess Gibbs free energy model, you do it once and you have it forever. It's just, in general, it's a little more cumbersome or tedious. Okay, so what we want to work out for the case of binary mixtures are some simplified equations that involve mole fractions. Okay, so how are we going to do it? Okay, well, the first thing we're going to do is we're going to recall our definition, or our Gibbs-Duhem equation for a system at constant temperature and pressure. So constant T and P, okay. So a constant temperature and pressure, okay. Our Gibbs-Duhem equation reduced to the case, or the equation, so our zero-sum requirement reduced to sum over I, xi, df bar I is equal to 0. So for the case of a binary mixture, we had x1 df bar 1 plus x2 df bar 2 is equal to 0. Okay? Our zero-sum requirement. Okay, point 1. Okay. Now the next thing we need to recall is, as we worked out in our partial molar property screencast videos, is that F, my molar F of my mixture, is equal to the molar average of the partial molar F's of the components of my solution. All right, so for a binary system, F is equal to x1 F bar 1 plus x2 F bar 2. Okay. What we're going to do next is work out an expression for the differential of f. Okay, so if I want the differential of f, okay, df would be equal to the differential of x1 f bar 1 plus the differential of x2 f bar 2. So now if I apply a product rule, okay, I would have then x1 df bar 1 plus f bar 1 dx1 plus x2 df bar 2 plus f bar 2 dx2. All right, so now looking back at my Gibbs-Duhem equation for my binary system at constant temperature and pressure, we have x1 df bar 1 plus x2 df bar 2 is equal to 0. If I look at my differential of f, which I just worked out, I see I have x1 df bar 1 and x2 df bar 2. So via the Gibbs-Duhem equation, the sum of these two terms has to be equal to 0. And so that leaves us with then df is just equal to f bar 1 dx1 plus f bar 2 dx2. Cool. All right, so now the next simplification we're going to make is x1 and x2. Okay, so I know x1 and x2 are related, right? x1 plus x2 is just equal to 1. My mole fractions sum to 1. So x2 is equal to 1 minus x1. So then it stands that dx1 and dx2 are also related. They are not independent of each other, right? We'll show dx2 is just negative dx1, right? So as the mole fraction of component 1 increases, mole fraction of component 2 decreases by an equivalent amount. Okay, so we know x1 plus x2 is equal to 1. So x2 then is equal to 1 minus x1. Okay, so these two terms are independent, so we're going to eliminate d2 in favor of d1, right? There's really no use having the two, right? They're the same. So if x2 is 1 minus x1, well then dx2 would be the differential of 1 minus x1, which is just negative dx1. So if I substitute that in, now I have the df is equal to f bar 1 dx1 minus f bar 2 dx1. Negative because it was a negative dx1. So now I could factor out a common dx1 term, and I get dx1 times f bar 1 minus f bar 2. Cool. Okay. And then the last step here is so df is equal to dx1 f bar 1 minus f bar 2. So if I divide by dx1, I have the df dx1 is equal to f bar 1 minus f bar 2. Okay, I'm going to box that in because we're going to build off of this. And even this is a pretty cool expression. So if I measure the partial molar f is a function of composition, and I compute its rate of change, the slope, right? The differential of f with respect to x1 at, constant t and p. So I measure, say, molar volume of a binary mixture as a function of composition. So now if I take the slope of, say, that curve, it's just equal to the difference in the partial molar f's of my two components of my mixture, right? Again, Gibbs-Duhem equation tells us our partial molar properties, or the change in our partial molar properties, and the partial molar properties themselves are related, right? They're not independent, okay? And it comes out in this equation. But I digress, okay? So now getting back on track. So what we're going to do next is we're going to go back, okay? And again, where this all started is, remember, f was equal to x1, f bar 1, plus x2, f bar 2, okay? And x1 and x2 are related, right? We showed that x2 was just equal to 1 minus x1. Okay, so again, I'm going to eliminate x2 in favor of x1. All right, they're related. No use in having the both of them in my expression. Okay, so I'm going to rewrite this as x1 f bar 1 plus 1 minus x1 f bar 2. So this could be x1 f bar 1 minus x1 f bar 2 plus f bar 2. Okay, and so I'm going to do here on this line then is now I'm going to factor out x1, or I'm going to collect in terms of x1 here, and I'm going to write this as x1 f bar 1 minus f bar 2 plus f bar 2. Okay. Great. Okay. Now what we're going to do is we're going to make a substitution. Okay. So here I have this term f bar 1 minus f bar 2, which also appears here in this expression that I have boxed in. So substituting in, that leads to f is equal to x1 df dx1 plus f bar 2. Okay, so now I only have one partial molar property left. So solving for f bar 2, I get that f bar 2 is equal to f minus x1 df dx1. So now I have an expression to calculate f bar 2 that only involves f and a derivative of f with respect to x1. Great. So if I have a function for f as a function, so if I have f as a function of composition, this now gives me a direct way in which I can readily compute it without making any substitutions whatsoever. All right? Awesome. Okay. Well, what about f bar 1? Well, if I want to get f bar 1, there's a number of things I can do. All right, and it's well, kind of up to you. Okay, so let's see what we might do. Well, one would be is here I have f bar 2. Okay, and so if I go up here, okay, so there's going to be several different ways you could simplify this. So, and actually I need to insert a new page. Okay, new page after. Okay, so there's a number of ways we can do it. So one is, okay, I have f bar 2 is equal to f minus x1 df1. Okay, if I come back here and I just write off to the side, okay, if I were to look at this equation, all right, I have that f bar 2 is equal to f bar 1 minus df dx1. Okay, df dx1. So what I could do is for f bar 2, sorry, pen's going wild. For f bar 2 down here, I could plug in f bar 1 minus df dx1. So if I write f bar 1 minus df dx1, okay, so f bar 2 is f bar 1 minus df dx1, got that, and that has to be equal to f minus x1 df dx1. So this is equal to f minus x1 df dx1. Okay, cool. So let me get some room. So let me bring this df dx1 over here. So f bar 1 then has to be equal to f minus x1 df dx1 plus df dx1. Okay, now here I'm going to factor out this df dx1. Okay, and I get f minus df dx1 times, okay, and this would be negative x1 plus 1. Okay, well, what is negative x1 plus 1? Well, I could equivalently write this as 1 minus x1. All right, so equivalently, all right, I write this as 1 minus x1. Okay, and I could leave it as 1 minus x1, but 1 minus x1 is also x2. So I get that f bar 1 is equal to f, okay, minus, and I'll write as 1 minus x1 df dx1, or equivalently, it's f minus x2 df dx1. Okay, groovy. Okay, so for binary system, we can work out these simplified expressions to calculate our partial molar properties in terms of derivatives of f with respect to composition, right? And this is going to be preferred because typically what I prefer to measure is my molar f, which is a function of composition, and so I'm going to fit models to it, which give it as a function of composition. Right? It's going to be much more generally applicable. Okay. Again, this is only the case for a binary system. If you have a ternary or higher, you're going to be stuck using our definition of our partial molar properties, where you make the substitution into, say, your analytic equation for f, the x1's n1 over n1 plus n2, or I guess if it was a ternary, n1 over n1 plus n2 plus n3, and so on and so forth. Okay, great.